Okay, in today's class, I'm gonna discuss design of quarter joints. So, design of quarter joint. Now, what is the purpose of quarter joint? The quarter joint is used to connect two rods. So, what you have is
Which one already guys? Wait.
please mute yourself.
Were we muted? Yes.
So, if you look at the quarter joint, this is how the quarter joint looks. So this is the rod. This is the same rod. So this is rod. What you have is you have something called the spigot end, and you have socket end. And then what you have is you have a hole, and what happens is this spigot end goes inside the socket end, and the collars, as you can see, these collars, they match, and then you hammer a quarter through it. The purpose of the quarter joint is to transmit the force. Quarter joint is not used for transmission of torque. What it means is reciprocating motion of the spigot end can be transmitted on the reciprocating motion on the socket side. So what are the typical applications of quarter joint? I want to give you a very simple example. Consider a steam engine. So steam engine has a cylinder. It has a piston cylinder type of assembly. And then what you have is you basically have a connecting rod that is attached from the piston side, the crank side. So you have a connecting rod, and this connecting rod is attached to the crank. So connecting rod is attached to the crank. Now, as you can see that you have this articulation at the crank, and you have this reciprocating motion of the connecting rod. And in order to transmit the reciprocating motion, in order to transmit the force, usually what you have here is you have a quarter joint. And if you look at the quarter, it looks something like this. Usually what we do is quarter is designed to be a weaker element. What it means is if this entire joint has to fail, we deliberately want quarter to fail. And there are some important dimensions, and what we are going to do is we are going to go step by step and design the most important dimensions of this quarter joint. And other dimensions, they come from first either the proportion or some sort of empirical evidence or maybe some engineering principles that would allow us to decide the other dimensions. So how do we design a quarter joint? Designing the quarter joint means finding out all the important dimensions of this joint. So what I'm going to do is I'm going to give you a step-by-step recipe for designing of quarter joint. And then if you want, I can work out an example. Just like what we did in the case of simple stresses, we are going to look at each and every cross section of this joint and see the potential ways that particular cross section could fail. So for an example, I'm going to take a cross section over here and see how would this fail. Then I'm going to take a look at cross section here. Then I would see how would this fail. Then I would take a cross section here. I would take a cross section here, and then find out the most important dimensions of this quarter joint. And once all these important dimensions are determined, you can actually draw a neat proportional sketch, and then you can use that sketch to actually create a CAD model inside a SolidWorks or maybe Autodesk software. And then you can use that to create an STL, and then you can 3D print it. Okay, so I'm going to start with step one. So step one is design of rod dia. Design of rod dia. Now, as you can see, there is this load P, and the same load P will get transmitted. So the rod dimension, this dimension D, will be decided based on the tensile or compressive failure. To design the quarter joint, we would know the load to be transmitted. Load is equal to P. Usually that is given in kilonewtons. It will give the value of sigma C, which is the crushing stress. We will know the value of sigma T. We would know the value of tau. So design of rod diameter. So this would be based on direct tension or compression. So if the load is P, so sigma T, because tensile stress is typically less than the compressive stress, P divided by pi by 4 T square. So from here, you can find out the value of the diameter. The failure area, the area, cross-section area will be the circular cross-section area. This is the diameter. Next thing, step two, is we want to find out the spigot diameter. Now I want you to take a look at this cross-section of spigot. So if I want you to take a look at this cross-section of spigot. If you look at the spigot, there is this hole that through which quarter needs to pass. So there is this hole. So if you look at the weakest cross section, the where that hole is, that is the weakest cross section. So if you look at spigot, spigot dia, if you look at the spigot dia, this is the cross section that is supporting the load. And as you can see, there is this hole. This is thickness of the quarter T, and this diameter is D1. Now the failure is also going to be again direct tension or compression. Direct tension or compression. And again, sigma T is equal to P. Now let's take a look at the area. You have the circular area, which is pi by 4 d1 square, and this area of the hole is d1 multiplied by T, where T is the thickness of the quarter. Quarter thickness. Now, one thing to observe that here there are two dimensions. There is D1 and there is T. So, and we just have one equation. So with one equation, we cannot find out two unknowns. So we need one more equation. And for that, we would consider the failure of quarter. So step 3. Step 3. And I'm going to call this crushing of quarter. Crushing of quarter. Now, what exactly happens when the quarter crushes in the spigot? I want you to visualize something like this. You have this quarter that is situated in between spigot, socket, and you have the quarter going in. And what you do is you apply a very strong pull. What's going to happen is the part of that quarter which is trapped in that spigot could potentially get crushed. In other words, you have applied the force and the resisting area, which is the diameter of the spigot multiplied by the thickness of the quarter, that area gets crushed. So the area, so sigma C is equal to P multiplied by D1 times T. That gives you the crushing of quarter. Now here, something important. Sigma C is the crushing stress. Crushing stress of quarter. So many a times, quarter could be made up with a different material than the spigot and socket. So when you are going to consider the failure of quarter, you have to take into account the failure stresses for the quarter material. So sigma C is the crushing stress of quarter. Now, from here, please understand, you will not be able to find out what is D and what is T. You will be able to find out the value of the product D1 times T. Everyone understood this? Once you use this equation, you know the value of P. Say P is 100 newtons. You know the value of sigma C. From here, you are going to find out the product, which is D1 times T. You would use this value, D1 times T, substitute in the previous equation, which is over here. So this comes from step 3. This comes from step 3, and then you should be able to get the value of D1. So from here, then you should be able to find out value of D1. Once you know the value of D1, then you can find out the value of T. So thickness of quarter to be known. So this way, now you have two dimensions at the same time. So next thing is we want to find out, which is step 4, is length of the quarter, or basically width of the quarter width. Now, what does this mean? So think about the quarter, and this quarter that is sitting inside the spigot could actually get sheared in double shear. So you could have the quarter that could get sheared, something like this. So this part goes one way, this part goes the other way. And now what you have is, you have this resisting area. So this is in double shear. Now here we have to make an engineering assumption. Please understand, the width of the quarter is not going to be uniform. Quarter has certain taper. So clearly the width on the top and width at the bottom is going to be different. So if you think about this width, I'm going to call this W1, and I'm going to call this W2. So you have W1 at the top, W2 at the bottom, and that quarter is actually taper. There is a reason the quarter is given a taper, because what you want to do is you want to hammer the quarter in. If the quarter is purely rectangular, the quarter will not fit properly and will not maintain the interference for the integrity of the joint. And you can think about it like, if the quarter is a rectangular quarter, there is no taper, then maybe little bit wobbly motion of the joint can throw that quarter off. That's why the quarter is taper, and then you hammer the quarter in so that there is a rigid joint between the spigot and the socket. So the assumption here is, this is the assumption. When we design the quarter width, I'm going to assume that there is a center width, which is the average of W1 and W2, and that is where the failure is going to take place. So I'm going to assume that this W is the width of the quarter, which is at the center point. So I'm going to say, considering double shear failure, tau is equal to P divided by W times T multiplied by 2. Please note, we already found out the value of T in the past step, which is step number 2. We found out the value of T. Substitute that value of T, substitute the value of tau for quarter, and then from here, we should be able to find out the width of the quarter. Now, next thing is, we want to see the spigot extension. So step 5, spigot extension. Now, this is an interesting failure that I want you to understand how this failure is going to happen. So if you look at the spigot extension, so I want you to visualize that the quarter can actually slice the whole thing. And what would happen is, this teeny tiny part of the spigot, and here is the quarter. So what happened? That quarter was in place in the spigot. Socket pulled the top and the bottom end of quarter, and that quarter kind of just sliced or sheared the spigot end. And this teeny tiny piece, which is the spigot, I'm going to call this spigot extension, and this is called as spigot extension L, which is called L L2. We got extension L2. And you can see that there are two areas, one on the either side. So tau is equal to P divided by 2 times L2 times, if you think about this dimension, this is the diameter of the spigot. And diameter D1 is already known. L2 is to be found out. And when you substitute this value, you will be able to find out what is the value of L2. But please understand, tau is the shear stress of the spigot, because we are designing the spigot. So we have to consider shear stress of the spigot. Any questions here? Next step. We want to find out the socket collar dia. So socket collar dia is this. So, oh, no, not this one. So let's go. This is the spigot. So socket collar dia is this guy. So this is the socket collar dia. And please understand that the quarter is going to be here. And this is an interesting failure. I want you to understand, visualize that you have the socket, you have the spigot, and you have the quarter, and both the rods on the either side, socket and spigot, they are pulled. And there is a possibility that the quarter may crush into the socket collar. And this diameter, I'm going to call this is D4. This is the diameter where the spigot rod sits, which is D1. And then if you look at from the side view, you would observe this is where it will be crushed. So sigma C is equal to P divided by D4 minus D1 multiplied by T. Now please note, yeah.
So does the hole for the keys usually go right all the way up to the socket collar?
So, okay, so what's going to happen is, let me show you the side view. And please ask any questions that you may have. So let me show you. This is, and then so the socket. So this is the spigot. This is the socket. And the quarter gets hammered in over here.
So the hole for the collar is flush with
Flushed with the,
socket
yes.
collar, but not the spigot collar?
So basically, the way you visualize is this hole gets flushed here. This collar rests against this collar, and I actually didn't show it. Basically, this would actually be aligned to the collar. So, in other words, the cotter is like wedged, fixed between the spigot and the socket. That's why when you pull, what would happen is that the cotter could crush the collar of the socket. Question?
So what's the collar on like the left side of the socket? Not on the right side next to the wall.
So let me show you. So there are going to be two collars. There is going to be a collar on the. Oh, actually, yeah. I drew this. Sorry. Yeah. You're right. I made a mistake here. Thanks for catching that. It's like this. I apologize. So this is how it's. Okay, does it make sense now? Okay. I think I drew this. Yeah, I drew this right, but I drew this wrong. Sorry. Yeah.
What about the inner diameter of the socket? Should we add gap or clearance?
Inner diameter of the socket? No, so inner diameter of the socket. So basically there will be some clearance, but not a whole lot, because this spigot diameter needs to go inside. So basically this guy will go something like this.
But they should not be the same, right? They can overlap, but they're the same.
No, there will be some clearance. You don't want them to be too big, otherwise it will be wobbly. They need to slide in and fit, and then you can hammer the cotter in.
How can we determine the clearance?
So usually those clearances are dependent on the type of fit that you want. And if you look at the design data book, there will be a hole and the dimensions of the hole, and there will be appropriate clearances that would be defined for particular type of fit. For example, in cotter joint, you don't want an interference fit. You don't want to hammer the spigot and socket together. You want them to be flush, but you don't want them to be loose. So it would be like a sort of a tap fit, like you tap it in and then it actually gets fitted. So if you look at the diameter of the socket, if you look at the diameter of the spigot, they will tell you the clearance that you need to have that particular type of fit. So there is a fit and interference table that you would follow from the design data book, and that actually tells you that how much tolerance that you should add. Any other questions? Yeah, online students, I unfortunately added the collar on the other side. So please make sure that this is how that socket looks like. Here I did it correctly. And that's why when you have the socket collar diameter, you have D4 minus D1 times T, and D1 is known, T is known. So from here, the only unknown is D4. Any questions here? Online students? Step 7. Now, next thing is collar width. So to find collar width, we have to consider collar in the double shear. And tau is equal to P divided by 2 times D4 minus D1 L4. So how does collar width come in the picture? So I want you to understand, just look at the same type of failure. And this quarter kind of slices through this section. And what would happen is, I want to show you the actual failure here. So imagine that this guy from here all the way up to here gets sliced off. And what you're gonna have? You're gonna have one piece over here. You're gonna have one more piece over here. And then the quarter that actually called the shearing sits over here. So now as you can see that this is L4. This dimension is D4. This dimension is D1. This dimension is L4. Yeah.
So that's just for the socket color?
Yeah, it's the socket color.
Is it for the spigot too or no?
No, we will do the, basically, we'll do the spigot little bit later. Let's finish with the quarter, and then the failures that are associated or caused by quarter, and then we will look at the failures of the spigot. Any other questions? Online students, everyone clear with the failures or how that joint is failing? Okay, the next thing is I'm gonna look at the socket, the failure of the socket. So step 8. So socket thickness. Now I want you to visualize this type of failure. Imagine that you have this rod, that actually rod comes out of the socket. So this is the thickness, and this dimension is L3. And please understand that we had the whole socket, but because of the some additional loading or some stresses, the rod part of the socket came out, and that failure is actually the circumferential shear. Please understand, the rod on the spigot side and the rod on the socket side, the diameters are the same. So this diameter is same as the diameter that we calculated. So tau is equal to P divided by 5 times D times L3. And D comes from step number 1, and tau is basically the shear stress for the socket. substitute those values, and then from here, you should be able to get the value of L3. Now, what we would do is we would move on to the Spigot. So this is step 8, step 9. Spigot, collar, dia, and Spigot collar dia is, please understand, Spigot collar dia would be because of the crushing. So crushing failure, and that is sigma c is equal to P divided by 5 by 4 d2 square minus d1 square, where d1 square we already found from step 2. And from here, you can find out the value of d2. Step 10, is Spigot, collar thickness, and I just want to show you the failure. So this is the Spigot end, and think about what would happen is this collar would actually slide through this rod. This collar, this is the rod diameter, this is the Spigot diameter, and this collar would actually slide through. So you would notice the potential failure is you have the collar, it is coming in like this, and you have the Spigot like this. And this is where the collar was supposed to be. And that is nothing but the circumferential shear. Everyone understood the type of failure? So basically, this rod slides through along with the Spigot, and then this collar comes out. And this thickness is L5. And that is okay. So these are the 10 steps. There is one more step, that is we have to check quarter for bending. And that step is a little bit involved. And many a times when you do this step, you would notice that quarter actually fails in bending. Now I want to emphasize, and before I do that, let me quickly go to the steps. So online students and in-person students, we are looking at the design of quarter joint, and I apologize for the mistake that I made. I added the collar on the other side, but this is how the socket and Spigot joint is supposed to work, wherein you have the Spigot end that fits inside the socket, and then the collars on the socket and the collar on the Spigot, they match. So collar on both sides, they match. And then you insert the quarter and that cotter is going to rest against the socket collar. And then once you have pulling and pushing type of loads, those loads would be transmitted from one side to the other side. Again, cotter joint is used for force transmission, not torque. So it's only transmitting the reciprocating motion. We are going to use the basic principles of stress and strain to find out the most important dimensions. Please understand, depending upon the design data book that you follow, some steps could be different. For example, if you look at some machinery's handbook, what they would do is they would give you a standard dimension of a cotter joint. So what it means is once you find out the diameter of the rod, the cotter joint, all the dimensions are decided proportional to that diameter. And you would notice that once you find the diameter, the entire cotter joint is designed. The reason for that is they did a lot of experiments and testing and empirical evidence, and they came up with the dimensions just to make sure that that cotter joint is safe. But as engineers, even though we know these proportions work, we have to check those answers. So if you follow some design data books, what they would do is they would ask you to find out the diameter of the rod. Once the diameter of rod is found out, the cotter width, cotter thickness, spigot diameter, diameter of the spigot collar, thickness of the spigot collar, all those dimensions are given in terms of the rod diameter. But still, we have to go and check just to make sure that that design is safe, it's not failing. Many a times, there could be slight variations in this design process. So for an example, in some design books, step 3 will be carried out first, then step 2. And then step 2 would be, and then the dimensions will be found out. Sometimes there will be slight variations based on the assumptions that you use for applications of these joints. But at the end of the day, you have to make sure as engineers, the joint that you have designed is safe in operation. It can withstand the loads, it can withstand the stresses, and then it can survive the operation or operating life that you prescribe. So step 1 is you have to find out the design of rod diameter. That is purely based on tension and compression. Tensile stresses are usually lower than the compressive stresses. That's why if you use the tensile stresses, your diameter would be slightly larger. So that's what we have used. Next thing is we have to find out the spigot diameter. Spigot diameter is where the failure of the spigot occurs, because that is where the spigot is weakened. Step 2 should be accompanied by step 3 because there are 2 dimensions. So you will need 2 equations. From here, you will find out the diameter of the spigot. You will find out the thickness of the cotter. Then you have to find out the width of the cotter. Cotter does not have a constant width. It has taper. So as an assumption, what we do is we assume the mean width, which is the average of top and bottom. Then we find out the dimension for spigot extension. And that spigot extension is found out using the shear failure. Then we find out the socket collar diameter. That socket collar diameter is the crushing of cotter onto the socket. Then we move on, and then we look at the thickness, and that comes because the cotter is shearing the collar. Then we find out the socket thickness, and then we find out the spigot. We go back to the spigot. We find out the spigot collar diameter, which is because of the crushing. And finally, we find out the spigot collar thickness. So these are the important steps in cotter joint. There is one last step which I want to discuss, which is we have to check quarter for bending. So last step, step 11, check quarter for bending. Now, if you think about the quarter is like a beam. So if you think about the quarter is like a beam. The central part of the quarter is in the spigot, and on the either side you have socket. So this part, this is in socket, this is in socket, and this is in spigot. So if you look at the load distribution, this is how the load is going to be distributed. Now, if I were to look at the dimensions, I can approximately find out these dimensions. This is D1, which is the diameter of the spigot. This is D4. So this is D4. Now, the load, this load is rectangular, and this load is triangular. And there is a reason these two different distributions are used for these two types of loadings. If you look at the quarter joint, you have the socket that is holding on the top and the bottom part of quarter. If you look at the spigot is holding onto the center portion of the quarter. So if you think about, if you were to visualize how that actually works, it is something like this. So it is assumed that the spigot is applying the load uniformly distributed at the center section, and the socket is applying the load which is uniformly varying on the either side of the quarter. That's why you have a triangular distribution on the left, triangular distribution on the right, and the rectangular distribution at center. I just want to show you. So if you think about it, this is, and then what you have here is, you have, this is the socket. Now we have to find out the maximum bending moment. How would we find out the maximum bending moment? There are two ways to find out the maximum bending moment. One way is to actually find out the distribution and find out the maximum value of the bending moment. Other way is to approximate the distribution and find out the value of the bending moment. I will discuss both these approaches, and depending upon which textbook you follow, both approaches are perfectly fine. So let's start with the load. If my load, total load, P is equal to total load. So what this means is this rectangular distribution is P. This triangular distribution is P by 2 and P by 2. So what I would do is, I have the rectangular distributed load at the center, and I have the triangular distributed load, half of the load on one side, half of the load on the other side. If I were to draw the free body diagram, if I were to draw the free body diagram, my free body diagram is going to look something like this. I'm going to have the maximum load here, and I have, please understand, I have a triangular load. The total load will be located at the centroid of the triangle. The total load will be located at the centroid of the triangle. So I'm going to have P by 2 over here, and I'm going to have P by 2 over here. Now, D4 is the diameter of the collar. So that dimension is known. D1 is known. So can you find out this dimension? This dimension can be found out. This dimension is going to be D4 minus D1 divided by 2. Same thing over here. Are you with me so far? Now I want to find out, since this is sort of a symmetric loading, when the loading is symmetric, my question to you would be, where would the maximum bending moment be? When the loading is symmetric, where would the maximum bending moment be? Maximum bending moment, you can draw the shear force diagram. You would observe that the maximum bending moment is going to be at the center. So what I'm going to do is, I'm going to find out maximum bending moment at section XX. So, sorry about that. So bending moment will be at section X. So how would I find out the bending moment? I have P by 2 multiplied by this distance, and check this out, this distance is going to be half distance D4 by 2 multiplied by, and this distance is going to be 2/3 from base, so 2/3 from here, minus D4 minus D1 divided by 2 multiplied by 2 by 3. So that gives me the moment because of this guy. This force is going up, so this bending moment is going to be positive. Any questions here? So what I'm trying to do is, I'm trying to find out the bending moment at this point. The bending moment at this point is the bending moment given by the triangular load and the bending moment given by the small portion of the rectangular load. Bending moment given by the triangular load is the total magnitude of the force, which is P by 2, multiplied by this distance. This distance is, this is D4 by 2 minus this distance, which is, this distance is D4 minus D1 by 2, and this distance will be 2/3 of D4 minus D1 by 2. So 2/3, that is going up. And then if you look at the rectangular portion here, this force is going to be, since at the center span, the load is P, half of that load is going to come down here, which is P by 2 minus P by 2 multiplied by this distance is d1 by 4. So as you can see that the total bending moment at the center span is bending moment given because of the uniformly varying load and then uniformly distributed load. Once you find out the bending moment, please note, you know the cross section of quarter. So I just want to show you how that quarter is loaded. So if you think about it, so that is how that quarter is loaded. Everyone with me so far on visualizing how the quarter is loaded? Now, this dimension is thickness T, and this dimension is W. So BM X divided by I multiplied by Y. Now, please note the bending is about this axis, which means BM X divided by T W cube by 12 multiplied by W by 2. And this should be less than sigma T of quarter. So that is how you would check quarter for bending. And that long expression that I have given you over there, you don't have to remember that equation. If you look at the textbook, that equation is given to you. Or many a times, depending upon the load distributions that you assume, that expression can be approximated as P times D4 divided by 4 or P times D4 divided by 6, depending upon the textbook that you use. Okay, this is how you would design a quarter joint. Any questions on the design of quarter joint? Yeah. Yes, W1 and W2, that is correct.
How do we find W1 and W2?
Okay, so the thing is, whenever you design, once you design the quarter will be given a center dimension W, and it will be given a taper. Now please understand, depending upon how hard you hammer the quarter down, that W1 and W2 could be different. So it's not exactly possible for us to find out what is the actual value of W1 or W2. But when you select the quarter, they will tell you this is the nominal width, and this is the nominal thickness, and this is the taper. And once you do that, you can actually use that quarter. Any other question? Yeah.
So I watched the version of this online. What's the socket diameter?
Socket diameter is this guy. Okay, I thought we didn't calculate. Okay, let me see, just a second. Probably I socket. Yeah, you are absolutely right. Oops. Okay. Oops. What I was thinking. Okay, I'll just explain to you over here. For some reason, the PowerPoint crashed. So socket diameter is this guy, and this dimension is dt. These are d3. So socket diameter d3 is in direct tension, and the direct tension is sigma t is equal to P divided by pi by 4 d3 square minus d1 square minus d3 minus d1 times t. So, and let me show you the failure. So if you look at this cross section, the cross section failure is going to be okay. Does it make sense? Any other questions? Yeah.
How do you know the length of the
Oh, length of the quarter. That's a good question. Length of the quarter usually is the diameter. This is D4 with some clearance on the top and the bottom. So usually you want to add about 5 to 10 millimeters clearance on the top and 5 to 10 millimeters clearance on the bottom. But length of the quarter is somewhere, quarter can extend outside the joint. So if you have, the quarter can extend outside the joint. Okay, any other questions? Yeah. Oh, that's standard. So if you look at the design data book, they will give you paper like 1 to 20, 1 to 24. And again, it depends upon the type of application you want. For example, for some heavy duty applications, the taper would be less, because what you want is so cotton is like a wedge. And remember, from statics and dynamics, you looked at the friction. So basically, that taper dictates the amount of force that you need to apply on the quarter to dismantle it. So depending upon the type of joint you want, that taper is given in the design data. So that is how. Yeah. Question online? Yeah.
I have a question.
Yes. For just a second. Yes. For quiz 1, choice is yours. So you can actually use quarter material same as the spigot and socket material. That is totally fine. Yeah. Any other question?
Yeah, do you mind, since all these joints are in our textbook, if we follow along in the textbook, the way some of the steps are a little bit in a different order, will we?
Yeah, that's fine.
Okay.
So, but please understand, you will have to make sure that you show that the design is safe. So, even if you follow the textbook and if you follow the same steps given in the textbook, that's totally fine. But I want you to understand that at the end, it's a design problem. There is no right or wrong answer, but your design should be the safe. Should be safe. You should check the design. Any other questions? So yeah, so basically D4 is the diameter of the collar and D3 is the diameter of the socket.
Yeah, in the video, in the recording about the cutter, it used D3 for the bending, but you used D4, so D4 what we should use.
Oh, actually, I don't remember what I used in the recording. So as long as you understand the failures, that's totally fine.
And then also the length of the cutter and the width, it says to use 4 times the rod diameter, which is what I used when I did mine.
That's totally fine. But if you want to see that 4 times the rod diameter would approximately be D4, that's about 10 to 15 millimeters.
Okay.
Because that is how the proportion is come about.
Okay.
Yeah.
So, because when I checked it for bending, when I went through it the first time, I used D3 instead of D4. And I could have done it wrong, but I thought that it failed in bending. What would we do in that case?
So now here is what happens. Almost always, you would notice the quarter would fail in bending. And there is a reason for that. Because when we talk about bending failure, there are 2 types of failures that we have in mind. Failure because of yielding and failure because of fracture. When we look at the failure in bending, what we assume that the quarter has exceeded its yield stress, which means it has deformed. But recognize that quarter might not have sliced off. Basically, it might not have failed because there's a yield point, upper yield point, lower yield point, and then there is a failure stress. So what this is telling us is even though the quarter has failed in bending, it has deformed, but that's okay. Because what we want that joint to remain rigid. So slight deformation is okay. So even if your quarter it's failing in bending, usually it would fail in bending. Just say that this is a fail-safe design. The quarter bending failure is because of yielding and not because of fracture. Everyone understood the logic behind this? So when we talk, there are 2 ways when we look at failure. One is the deflection-based failure, and the other one is the strength-based failure. Quarter has failed. What that means has quarter actually sheared, quarter basically fractured. That is one type of failure. The other type of failure that we can see is quarter has bent. But even though the quarter is bent in this particular assembly, still that assembly could function. In fact, what we want is if the joint exceeds its rated capacity, if the joint exceeds its rated capacity, we want the first element to fail is quarter because we can replace it. That's why even if you see that your quarter is failing in bending, that's okay. Just leave it as is. So basically, you have to provide the tolerances to the most important dimensions, and the most important dimensions are the dimensions that are making that assembly. So for example, the rod diameter, the spigot diameter, then those are the most important dimension. If you look at the outside diameter of the collar or the thickness of the collar, they are not assembly dimensions. So this is another interesting question. Like, too much tolerancing is bad because it will increase the cost to manufacture. And so what you want to do is you want to specify the tolerances that are essential for operation. At this point, I want you to think about this particular joint. What are the most important dimensions that would ensure smooth assembly? One is the rod diameter that has to be defined. Socket diameter, inside diameter has to be same as the spigot outside diameter that has to be defined. Quarter width, quarter thickness, those are important dimensions because those are assembly dimensions. If they don't have proper tolerances, then the whole joint cannot be assembled. Then the next dimension comes is the thickness. Thickness of the collar is not an assembly dimension. So you don't have to have very high tolerances on the thickness of the collar. Outside diameter of the collar, it can have slight oversized dimensions. That's totally fine. So the most important dimensions that should have tolerances are the dimensions that will facilitate assembly. Does that answer your question, Alexander?
Just by general practice in the industry, when you're doing stress analysis, you always go to the lowest values, or I guess, perspective to.
Okay, so again, this is an important question, and I just want to tell you upfront. When you go to industry, you are not going to design the quarter joint the way I showed. What we are going to do is we are going to just find out some basic dimension of quarter joint and look at the catalog items and select a CAD model of that quarter joint. Import that CAD model inside SolidWorks or Autodesk and then apply finite element analysis, some sort of modeling techniques, and find out the stresses and make sure that joint is safe. Because please understand, here we have not considered the action of combined loading. So what we assume that, hey, this rod is just failing in tension. That's not true. That rod is subjected to tension, subjected to compression, subjected to shear, and because of all that stuff, there will be principal stresses that we are not considering at all. Because it's not possible to do those types of detailed analysis for a three-dimensional structure by hand. So what you would do is you would follow these basic guidelines, come up with some basic dimensions, select the catalog item, and perform the finite element analysis inside the software. That's why one of those exercises wherein I asked you to perform finite element analysis. That is how you will design when you go to industry. But you need to know that what are the types of failure that this joint must absolutely prevent. Let me give you an example. This is a single quarter joint. You would go and you would see a double quarter joint. A double quarter joint means you have just one socket and then you have two spigots on either side. Design procedure exactly same. You design the half of the joint and then just duplicate that joint onto the other side. And there's an example in the textbook where you have used the double quarter joint. So there could be variations of the quarter joint. And we will look at the knuckle joint, wherein instead of a quarter, what we have a pin, and then we would actually perform the similar type of analysis. And at the end, all these mathematical tools, these basic mechanics of material principles will give you confidence to design using the solid modeling software. And that's what you would do when you go to industry. But fundamentals should be clear. This is how the joint. Okay, I'm gonna stop here. And if you have any questions, let me know.